In this video, I'm going to introduce intermolecular forces and talk about one specific type of intermolecular force, and that is dispersion forces. So, to review, an intermolecular force is a force of attraction that exists between covalent molecules. And this is a picture of an intermolecular force here. If we look at this diagram, we see we have two HCl molecules next to each other, hydrogen chloride, and this dashed line right here, this represents a force of attraction between the molecules, between the chlorine of this molecule on the left and the hydrogen of this molecule on the right. And this results from the fact that this chlorine is partially negative and this hydrogen is partially positive. So they attract each other. And these intermolecular forces help to explain why certain substances are solids at room temperature, why others are liquids at room temperature, and why others are gases at room temperature. So we should recall that gases are compressible, and the word fluid is referring to the fact that the molecules are moving and the substance can change its shape. So gases are compressible fluids, and the molecules have space between them. Like gases, liquids also have particles that are moving, but they're not compressible. They're incompressible, as in they always take up the same amount of space and you can't compress them if you push on them. And the molecules are tightly packed. This is another difference between liquids and gases. They're incompressible and they're more tightly packed. Solids also have have particles in close contact, but the molecules in a solid do not move. They vibrate in place, and they're rigid. So if we compare the forces of attraction between the molecules in a solid versus a liquid versus a gas, we would expect that because solids have particles that don't move and are locked in place, that the attraction between those particles is going to be high. So solids have the greatest force of attraction between particles, and therefore gases are going to have the weakest. Gas particles have little to no attraction to each other, which is why there's space between them, and they don't attract each other. This is a review of how substances can change phase. So we're most familiar with solids melting into liquids and liquids boiling into gas, but we should recall that gases can also condense into liquids and liquids can freeze into solids. We also have these two phase changes that occur when a gas goes directly to a solid. That's called deposition. And the phase change that occurs when a solid goes directly to a gas is called sublimation. Question 3. What is the relationship between the strength of the forces holding a substance together and its relative boiling and melting point? Well, if something has strong forces holding it together, that means it's going to be hard to boil that substance. The boiling of a substance means that you're freeing molecules from the liquid. And to do that, you have to give it enough energy to get those molecules away from the surface of a liquid. So molecules with strong forces of attraction tend to have high boiling points. And they also tend to have high melting points because when we're melting, we're going from a solid to a liquid. So if we want to melt a substance, we have to break those bonds between those solid particles. And if we need a lot of energy to do that, that's because those molecules have strong forces of attraction. And this is a direct relationship. Stronger intermolecular forces lead to higher boiling points and higher melting points. And in this unit, we're studying 3 types of intermolecular forces: dispersion forces, dipole-dipole forces, and hydrogen bonding. This video is going to focus on dispersion forces. I'm going to make another video for dipole-dipole and hydrogen bonding. And we'll focus on how these intermolecular forces can explain the properties of substances. So what is a dispersion force? A dispersion force is a weak attractive force that is caused by a distortion of the electron cloud surrounding an atom or molecule, which creates what we call a temporary or an instantaneous dipole. And there's a lot in here, so we're going to be unpacking this definition in the coming slides. But a key thing to realize already is that these dipoles are instantaneous. They exist for fractions of a second, which is why these dispersion forces are very weak. They are our weakest intermolecular force. So we can visualize this if we have two molecules, which are shown here. And when this molecule gets approached by another molecule, the electrons are moving randomly. And that means that just due to the random movement of electrons, the electrons can cluster on one side of the molecule. So this side becomes partially negative for just a fraction of a second over here. And then this side becomes partially positive because it's a molecule. So there's still atoms with positively charged nuclei on this side of the molecule. So that's why it's partially positive. All the electrons are over on the left side. And this then causes neighboring molecules to also have a temporary dipole. Because if this atom approaches this molecule, if this molecule approaches that molecule, then the partial positive here can attract electrons to this side of the neighboring molecule. And that makes this side partially negative. And now, because we have partial negatives and partial positives, we have a force of attraction. The original dipole was our temporary dipole, and then the other one we call an induced dipole, just because it was a dipole created by this neighboring molecule. But both of these dipoles are temporary and instantaneous, and they result in a force of attraction that we call a dispersion force. Okay. So these molecules are now attracted to each other because of these temporary dipoles, because of the random clustering of electrons on one side of the molecule. And this gives us a dispersion force, shown here with the dotted line. This is another way to think about an instantaneous dipole. Notice up here we have our electrons clustering on one side of the molecule. This little blue guy is our nucleus. So he has all of the electrons just for a fraction of a second. But because electrons move randomly, in another moment it might shift and the electrons might cluster around the other nucleus. But in both cases we have a dipole. On the left side, this is the more negative side of the atom. And over here, this is the more negative side of the atom. So these are what instantaneous dipoles actually look like. And they result from electrons moving randomly. Okay, this question. Draw the structural formula of two molecules of hydrogen. Identify the covalent bonds with a solid line and the dispersion forces with a dashed line. So we learned how to draw hydrogen last unit. So we can draw a hydrogen molecule just like this. Remember, there is one pair of electrons being shared between these hydrogen atoms. And because of the fact that electrons move randomly, sometimes electrons might cluster around one hydrogen. So it might just happen that this hydrogen ends up partial positive and this hydrogen ends up partial negative, just because of the random movement of electrons around these molecules. And this would give us a dispersion force. This would be our dispersion force. Okay? And that's shown again on this next slide. Okay? So that's our covalent bond between the hydrogen atoms, and then the force of attraction between them, between the two molecules, our intermolecular force, is our dispersion force. Okay, so now we have a sense of what dispersion forces are. Again, they're our weakest intermolecular force, and I haven't said this yet, but they're found in all molecules. All molecules have dispersion forces. And the strength of dispersion forces depends on a few different properties of molecules. Dispersion forces are affected by the mass of a molecule. So larger molecules tend to have stronger dispersion forces. Dispersion forces are affected by the distance between two molecules. They tend to increase as molecules are brought closer together. And the strength of dispersion forces are affected by the surface area of molecules. So the strength of those dispersion forces tends to increase as the surface area of molecules increase. We're going to go over why this happens, how we can explain these. So the first one is mass. Why is it that molecules with larger mass have stronger dispersion forces? Well, the short answer is that they have more electrons. And if you have two large molecules next to each other with a large amount of electrons, then they have huge electron clouds that can shift back and forth. And this creates larger dipoles. We say that they are more polarizable because there are more electrons that can shift. And this can result in a greater strength of dispersion forces. Because the partial positives and the partial negatives are larger, the more electrons there are in the electron cloud. And this, in turn, is an extension of Coulomb's law. Because remember, Coulomb's law says that our nucleus is attracted to our electrons. And if we have more electrons, then Q2 will be a larger number, creating a greater force of attraction between neighboring molecules. Another factor that influences the strength of dispersion forces is how close together molecules are. And this is also as a result of Coulomb's law. As you bring molecules closer together, then there is going to be less distance between them. And there's going to be more shifts in the electron cloud. And the strength of the dispersion forces will increase. So the closer you bring molecules together, the closer those charges get to each other, the more the electron cloud shifts, and the greater the strength will become. The last factor that influences the strength of dispersion forces is surface area. And molecules with larger surface area tend to have stronger dispersion forces because there's more places for molecules to contact each other. Remember, IMFs are between neighboring molecules. If molecules can contact each other in more places, then they're going to be more strongly attracted to each other. You can think of it like Velcro. The larger your piece of Velcro, the stickier it's going to be. Here's two molecules, N-pentane and neopentane, that have the same chemical formula, but their boiling points are different. Notice that our N-pentane has a boiling point of 36, while neopentane has a boiling point of 9.5, even though they both have the same formula, C5H12. The way we can explain that is because the dispersion forces in N-pentane are larger because it's a longer molecule with a greater surface area. Two N-pentane molecules have more points for dispersion forces to act compared to two neopentane molecules, which, due to their roughly spherical shape, can't contact each other in as many places and therefore can't create dispersion forces that are as strong. And this is all to review dispersion forces. As I said, these are present in all covalent atoms and molecules. Sometimes they're not predominant, meaning that there may be another stronger IMF present, so that the dispersion force isn't ultimately what determines that substance's properties, but it's still there. And it's the weakest of all the forces, so it takes the least energy to break. Substances that only have dispersion forces tend to boil very easily, and a lot of them exist as gases at room temperature because they don't take much energy to break those forces. And it is the only IMF that exists between nonpolar molecules and neutral atoms. So an example of a nonpolar molecule would be something like oxygen. Oxygen is nonpolar because it's symmetrical and there's no permanent dipole. But this can still form an instantaneous dipole, and thus there can be a dispersion force between neighboring oxygen molecules, right? This would be our dispersion force between our neighboring molecules, each with their electron clouds. It's also the force that exists between neutral atoms like noble gases. So this is sort of a technicality, but a noble gas like neon is not a molecule. It exists as single atoms because noble gases don't bond. But it still has an electron cloud. So two neighboring neon atoms could still have a dispersion force between them because their electron clouds can shift. Okay, I hope this was helpful, and I'll be making another video about dipole-dipole forces and hydrogen bonding.